All right, here's another example from Beer Johnson. We have an 18-pound block. It slides in a vertical frictionless slot, and it's connected to a moving base right here. By means of a spring that has a constant of 8 pounds per foot, knowing that the acceleration of the support is this, right? So we have A is equal to 5 times the sine of 6 times t, and these are in feet per second squared. We want to find the displacement, maximum displacement of the block, and the amplitude of the fluctuating force exerted by the spring on the block. Okay, so the first thing I might want to do is find my natural frequency and then compare it to the forcing frequency, right? So this is going to be K over M. The K is 8. The mass is 18, but divided by 32.2. So we put it back up in the denominator. So we get a natural frequency of 3.783 radians per second. So our R is omega F over omega N, or 6 over 3.783, which gives us a 1.586. Let's see, other things. We can find our magnitude of the acceleration or the amount of motion of this piece, because we do know that it's, we working backwards, if we had, let's call it y, we often call it y, or I guess maybe we'll call it del. If we had del is equal to del m sine of omega f t, then we would get, del dot would be del m omega f cosine of omega f t. And then we get del double dot, which is the acceleration. We get negative del m omega f squared sine of omega ft, right? So we can see that right here what we have as am is going to be equal to del m omega f squared. So therefore, if we want del m, we could get am and divide it by omega f squared. I could have just written that, I guess, but I wanted to walk it through. So we get 5 divided by 6 squared. And so we get a 0.1389 feet is the magnitude of the motion of this piece. Now we know from base motion that we can have the motion of this is going to be related, when we have no damping, to 1 minus r squared. By the way, that's a absolute value thing going on right there. So we go ahead and plug them in at 0.1389, 1 minus 1.586 squared, and we're going to get 0.09164 feet. We will probably would want that in inches. So divide by or multiply by 12 and you get 1.100 inches. And if you looked it up in the back of the book, that would be the answer. Yay. We'd also note something, that if we have, we take a look at these magnification factor, we would have like, boom, here's 1, right there. That we would be over on this side because of this value, which means we are out of phase. Something to consider. couple things we could do about the force, amplitude, force exerted by the spring on the block. Boom, right in there. I think the best way to approach this is to just think about it's a spring that is being deflected. How much is it being deflected? Well, it's going to be deflected by the difference between, okay, because these are out of phase, that's part of the thought. So the out of phase thought process on here is that when this thing is moving upwards, that's moving upwards, this guy is moving downwards, right? So we're going to have the most amount of spring. So the force being transmitted between them is going to be the del M plus the X. And so you're going to have a 8 times your 0.1389 feet plus your 0.09164 feet. So your force, and I might actually call this FT. We'll call it the transmitted force. Kind of is. No, it's not. That's really actually. Truth is that this is the this would be the force up in here. Actually, I think that would be the same. Yeah, they'd be the same. I'm sorry. They do a free body diagram of the spring. It had to be the same. 1.844 pounds. So boom, there you go. 11:47 at night, and we have many long ways to go before we can go to sleep.